Hi, welcome back. This is Professor Ridge and today's lesson on section 8.9, polynomial and rational functions. So example 1, we want to solve x squared plus 3x minus 10 is greater than 0. And the first technique we're going to discuss is looking at the graph. So consider the related equation. So if we look at this related function, f of x is equal to x squared minus, or x squared plus 3x minus 10, and the idea is we're looking for x values that the y value, f of x is the y value, is greater than 0. So we want y values to be positive. Now if we think about a graph, y equals x squared plus 3x minus 10, and we know that's going to be a parabola, and if we were to solve it, to find the x-intercepts, you're going to let the y value equal 0, and so factors of 10 to subtract the 3 are 5 and 2, bigger one's positive, set each of those equal to 0. So our x-intercepts are negative 5 or positive 2 on the x-axis. So that's negative 5, 0, and 2, 0. I should say or. Okay, so negative 5, 0, and positive 2. And this is a parabola that opens up. And I don't care too much about the exact graph and where the vertex is. I certainly can figure that out. But the idea is this is the parabola y, or f of x, equals x squared plus 3x minus 10. And the idea is we want the y values to be positive. Now if I think about the graph, that means above the x-axis. Okay, so you can see that right here, this portion of the graph is above the x-axis, and so is this. But the solution to the original problem are there's no y in it, it's just x values. So basically you look at the graph and you can see that this part here and then the part over here would be the solution. So my solution is going to be, just looking at the graph, is going to be negative infinity to the original problem. So x squared plus 3x minus 10 is greater than 0 when x is less than negative 5. These should be open circles. Or when x is greater than 2. So negative infinity to negative 5, union to infinity. So that would be the solution. So if you have the graph, it's pretty simple. And notice I didn't graph it exactly. I just knew it was a parabola that opens up because the leading coefficient's positive, right? Y equals x squared opens up. Y equals like negative 3x squared would open down. Y equals 2/3 x squared would open up. So you look at the x squared part. This tells me it's positive, so it opens up. Alright, so let's try another one. Alright, let's look at exercise 9, just see if you get this idea of looking at the graph. It says solve using the graph provided, and they tell us that this polynomial, this graph is p of x squared equals x to the 4th plus minus x cubed, x to the 4th minus 3x cubed minus 4x squared plus 12x. Okay, so that's the graph that they provide us. And the idea then is we want to solve this thing here, x fourth plus 12x is greater than 3x cubed plus 4x squared. Now the idea is we want a landmark. Remember, the x-axis is y equals 0. So if we can get this polynomial p of x to be equal to 0, that's going to be these 4 points where the y coordinate equals 0. So negative 2, 0, 0, 2, 0, and 3, 0. So we have 4 x-intercepts. So that's where the polynomial equals 0. Now, if we look at the inequality we're given, you can subtract 3x cubed from both sides, subtract 4x squared from both sides, and then you get that greater than 0. So this is our p of x, and we're going to look at the graph and say, where is it greater than 0? So again, that's positive. Oh, not greater, right? We want p of, okay, so we want p of x to be positive. Where are the y values above the x-axis? So above our y values. So what x values give you y values that are above the x-axis? So that's kind of the way we think of it. And if you have the graph, it's super easy. So let's see. Above the x-axis would be this portion. So this from negative 2 to 0. And then it would be this portion here. So, and then of course this piece here. So the solution to this original problem will be from negative infinity to negative 2, sorry, between 0 and 2, and from 3 to infinity. So it's simple as that when you have the graph. Okay, so that's one method if you think about the graph. So if you know what the graph looks like, or you have some easy way to get the graph using a graphing calculator or such, you can just look at it and see real quickly where it is. Now if we wanted to solve one to be less than 0, then obviously the solution would have been the other points, the parts that are below the x-axis. So less than 0 would be negative. And then if it's greater than or equal to 0, then you just include the endpoints where it's equal to 0. So then these would have brackets for the endpoints. Alright, so let's learn the next technique, next page. Okay, so the next technique is, if you don't want to think about the graph, what you can do is your first thing is figure out, well, where is it equal to 0? So we call those critical points. So you're going to find critical points where it's equal to 0. So we're going to solve equal to 0. So where is it equal to 0? You just set each factor equal to 0. Well, first you would have to factor it if it wasn't factored, which in this case it is. So x is 6, or x is 5. And then what you do is now, so your first step is you're going to get the critical points of where it's equal to 0. Then you're going to draw your number line. Place your critical points. So we're going to draw a number line. Now what I do, if equal to is part of the solution, then I make these solid dots. If it's not, I make them open dots. So here's 5, here's 6. Open circle, open circle. And this splits the number line into 3 pieces. So we have an interval. You're going to pick a number in this interval. This is our next one, is we're going to test each interval. So pick a number that's between negative infinity and 5. So let's try 0. So let's say x equals 0. Pick a number in this interval. So let's say x equals 5.5. And then we're going to pick one in this interval. Pick a number from 6 to infinity. So let's say x equals 10. Now we're going to plug each one of these numbers in and test each interval. So we go back to the original problem. So we're going to put in 0 minus 6. So we're testing the x equals 0. 0 minus 5. And you want to check, is that less than, so question mark, 0? Yes or no? So I got negative 6 times negative 5, which is 30. So that's false. Okay, so now we're going to test the middle interval. So we're going to test x equals 5.5. Plug it in. So 5.5 minus 6. 5.5 minus 5. That's going to give me negative 0.5 times positive 0.5, which is negative 0.25, which is less than 0. That's true. And then we test the last interval, 10 minus 6 times 10 minus 5, which gives me 4 times 5, which is 20. Is 20 less than 0? That's false. And then you're going to, then you just include the true intervals. So the true intervals is the solution. So you just have to pick one point inside each interval. Okay, so in this case, the solution's only the numbers between between 6, between 5 and 6. Okay, so any numbers between 5 and 6, that's the solution for this one. And again, if I would have looked at the graph, again, it's a parabola, opens up, and then I could have seen that also. All right, let's try another one of these. Yeah, so just include the endpoints in the intervals if you use if it's less than or equal to or greater than or equal to. And the equal to are the endpoints. So if you use either less than or equal to or greater than or equal to, then you would put brackets on the and include the endpoints. All right, let's try another one. Okay, so our first thing is figure out where it's equal to 0. So we set it, both of those factors equal to 0. So x equals negative 7 or negative 2 or positive 2. So I'm going to make my number line. Negative 7. You don't have to scale it. You just have to make sure that you have them in the right relative position, left and right. Okay, so negative 7, I'm going to put solid dots, again, because of the equal to. So those are going to be part of my solution set. So I'm going to have brackets when I write my interval notation. Now I'm going to pick a test point in each interval. So like I'm going to pick x equals negative 10, x equals 0, and maybe x equals 4. Now I'm going to plug these into the problem. So let's see. Negative 10 plus 7 times negative 10 minus 2, is that greater than or equal to 0? Question mark. So we get negative negative 3 times negative 12, which is positive 36. And I don't really care about the number. It's positive. Positive is greater than 0. So this part's true. So that part's part of the solution set. And then I plug in 0. Let's see. 0 plus 7 times 0 minus 2, which is 7 times negative 2, which is greater than or 0, false. Because negative 14 is not greater than 0. So I don't shade that interval in. And then the last check would be 4. 4 plus 7, 4 minus 2. So that is 11 times 2, which is 22. That's true. So that piece is part of the solution. And my solution is from negative infinity to negative 7. I'm going to include the endpoint, union to infinity. And of course, infinity, you can never get there, so always has a parenthesis. Alright, so that's pretty much how you do it using that technique. Let's try number 18. Alright, so we got x squared. Okay, so our first step is we have to factor it to figure out where it's equal to 0. Factors of 2 that subtract the 1. Put in our signs. And then we're going to set these equal to 0 for our critical points. So x equals negative 2 or x equals 1. Make my little number line. Negative 2. And again, I don't really have to scale it. I'm going to put open circles because there's no equal to. It's just strictly greater than or less than. This case is strictly less than. Okay, pick a number. See, it splits the number line into 3 intervals, 3 pieces. Pick a number in each interval. So let's pick x equals negative 3, x equals 0, x equals 2. And let's plug it in. So for this one, let's use the factored form. We can plug it in the original one too if we wanted to. But I'm going to plug it into the factored form. So negative 3 plus 2, it's just a little easier to do the calculation. And again, technically I don't even have to figure out the numbers. I just have to know that, hey, negative 3 plus 2 is a negative number. Negative 3 minus 1 is a negative number. You know, whether I write negative 1 and negative 4, the negative times the negative is positive, and is positive less than 0? And the answer is no. That's false. So, I mean, it's up to you whether you actually figure out the exact number, right? Whether you went negative 1 times negative 4 is positive 4, which is not less than 0. Or, you know, all we care about is positive, negative. So you can just forget the number, just make sure you get the sign right. Okay, so if you understand that, that's a little bit of a shortcut. So like here, you know, 0 plus 2 is positive. 0 minus 1 is negative. Positive times a negative is negative. And is a negative less than 0? Yes, so that's true. Now if you don't totally understand that, go ahead and use numbers and just, you know, ask yourself, is true or false. So that's actually part of the method that the book will show you, is what they call it the sign. You know, you're analyzing the sign. And that's another way to do it also. So, and we can kind of blend these two techniques and do a test point, but just write down the sign. So if x is 2, we get 2 plus 2, 2 minus 1. And again, that's going to give me positive 4. Here, I'll do it with the actual numbers this time. Positive 1. Positive times the positive is positive. And if you prefer, you can write 4. See, positive 4, positive 1 will give me positive 4. Positive is less than 0. That's false. So our solution set is just the interval between negative 2 and 1. There you go. Okay, so we can extend this technique to as many factors as you want. So if you look at number 25, we have, it's already factored for us, so that's nice. We have 3 factors, so that's going to give us 3 points, 3 x-intercepts. So we're going to set them each equal to 0, find those critical numbers. So we're going to get x equals 1, x equals -2, x equals 4. So when I do my number line, I'm going to get 4 intervals. So again, we don't really have to worry about scaling, but you do have to put the right relative position. So we got -2, 1, meaning the smallest number all the way to the left. Now these are going to be solid dots because of the equal to. And again, if I just think about sign, greater than 0 is positive, or equal to 0. The equal to 0 are the dots, those points exactly. Now I got to test each interval. So let's test x equals -4, x equals 0, x equals 2, x equals 10. So let's see, and then we're going to put them in there. So we get -4 minus 1, -4 plus 2, and -4 minus 4, which is going to get me, again, I just care about the sign, negative times a negative times a negative, which equals a negative number. And so that's going to be false, because I want positives. The middle, x equals 0, so I put it in. I'm going to get 0 minus 1, 0 plus 2, times 0 minus 4, which is going to get me negative, positive, negative, which equals a positive. So that's true. So it's this piece. And then I check the next one. So for this next interval, I'm going to do 2, so it's 2 minus 1, 2 plus 2, and 2 minus 4, which will get me positive, positive, negative, which gives me a negative number, which is false. And then for 10, I'm going to get 10 minus 1, 10 plus 2, times 10 minus 4, which will be positive, times a positive, times a positive, and that's going to be true. Okay, again, I just care about positive and negative because to be greater than 0 is a positive number. And if you want, you can figure out the exact number, but we don't need to. We just need to know, is it true or false? So we can just analyze the sign. So our solution set is all the numbers, all the x values between -2 and 1, union all the x values between 4 and infinity. So those 2 intervals, which is a whole bunch of x values, right? Okay, so let's look at number 28. It says find all the x values, or for f of x, which equals 14 minus x squared, find all x values for which f of x is greater than 5. So if we start with this inequality, and we're going to replace f of x, which 14 minus x squared, and then we're going to get it equal to 0. Okay, and then we can factor that. That's the difference of squares, 3 plus x, 3 minus x. And then our x-intercepts would be 3 minus x, or 3 plus x is equal to 0. 3 minus x is equal to 0. So this would be x equals 3. This one we'd subtract 3, so you get negative x equals -3, and then divide both sides by -1. So x equals 3. Or you can just add x to both sides and get here just as quick. So this one was negative 3 and this one's positive 3. So now we're going to make our number line. Negative 3, 3. Pick a test point in each interval. X equals negative 5, x equals 0, x equals 4. We're going to plug it into... Now we could plug it into the original equation and see if it's bigger than 5. So the original, if I did f of negative 5, in the original problem, 14 minus negative 5 squared is what? 14 minus 25, which is negative 11. And is that greater than 5? No, that's false. F of 0 is, what is f of 0? F of 0 is 14 minus 0 squared, which is 14. Is that greater than 5? True. So we know these are open circles because it's just greater than, not greater than or equal to. And then we just got to test that last portion, which would be f of 4 would be 14 minus 4 squared, which is negative 2. So that would be false. Is that greater than 5? That's false. Alright, so our solution set would be between negative 3 and 3. Okay, now we got to do rational inequalities. So let's do that one on the next page. Okay, so on this one, for our critical numbers, it's basically where is it equal to 0? The top, and basically that's what the top is, equal to 0. Because if you solve this, you multiply by the denominator on both sides, and the denominator goes away. 0 times anything is still 0. So then you set these equal to 0. So the shortcut, just take the top, set it equals 0. But it's the same technique. We're finding out where is it true, where is it equal. And then add 1. So x equals 1. But then you also got to consider where it's undefined. You know, what's the domain kind of question, where is it undefined, and where a fraction is undefined is when the denominator is equal to 0. So x equals negative 3. Now, note, on this one is always going to be an open circle. Okay, so we make our number line, and this is greater than or equal to, so the equal to parts are solid, and we got 1 way over here, solid dot, that's equal to, and then negative 3, that's going to be an open circle because it's undefined there, so you can never be equal to if it's undefined. So that's what I'm saying, it's always an open circle. Okay, so we got 4 intervals now, so we got x equals, say, negative 5, x equals negative 3.5, x equals 0, x equals 2. And we're going to plug them into the inequality. And again, I can just look at the sign. So for x equals negative 5, we're going to get negative 5 plus 4, negative 5 minus 1, over negative 5 plus 3, which will give me, let's see, negative divided by a negative, which equals a negative number. And that greater than 0 is false. Now we check the middle one, x equals negative 3.5. Do the same thing. And again, we just care about positive or negative. Positive, negative, negative, which a negative divided by a negative is positive. So you just count. There's 2 negative signs, that makes positive. 3 negative signs, it's negative. So if it's an odd number, negative signs, negative. An even number, this has 2, so it'll be positive. And positive is greater than 0. True. So that piece is true. And we got to test the next piece, x equals 0. And it's going to be 0 plus 4, which is positive. Just to save space, I'm just going to write 0 minus 1 is negative. 0 plus 3 is positive. Negative divided by a negative divided by positive is negative. So this would be false, because negative is not greater than 0. Then we check the last interval, x equals 2. And that's going to be positive. 2 plus 4 is positive, 2 minus 1 is positive, 2 plus 3 is positive. So everything's positive, so that's going to be positive, which is greater than 0, so that's true. So then our solution set would be, oops, got to use the right, negative 4 to negative 3, parenthesis, union, bracket, 1 to infinity. Okay, and then the last one, let's try number 44. And this one, x over x minus 1 is greater than 2. Now there's 2 techniques you can use here. You can subtract the 2 so you can get it to 0, and then do exactly what we did and make it then get one fraction, combine them to make one fraction, and then do it just like we did number 40. Or we can just go with it this way, and our critical numbers are still the same thing, where it's equal. Now since it's not equal to 0, we got to do like this, and you're going to cross multiply, or you're going to multiply by the LCD. So you're going to get x equals 2x minus 2. Let's see, subtract 2x. So we get negative x equals negative 2, so x equals 2. And then where it's undefined, is still going to be where the bottom equals 0, so x equals 1. So we're just going to have x equals 1, open circle there, x equals 2, and it's going to be open circle since it's just strictly greater than. There's no equal to in it. Then we're going to test each 3 regions here. X equals 0, x equals 1.5, x equals 3. Now here, if we're going to leave it the way it is, we actually got to calculate the numbers, because greater than 2 is not 1 is greater than 1 is positive number, but it would be false that it's 1 is greater than 2. So we actually got to work out the details here. So x equals 0. We're going to get 0 over 0 minus 1 and ask the question, is that a true statement or a false statement? 0 greater than 2, that's false. Pick one in the middle. You're going to get 1.5 over 1.5 minus 1, which is 0.5, which is 3. And is 3 greater than 2? And that's true. So we want that piece. And then we do the last piece, 3 over 3 minus 1, which is 3 over 2. Is that greater than 2? Question mark. And the answer is no. 1.5 is not bigger than 2. So our solution is just between 1 and 2. And there's no equal to, so we leave it like that. Alright, so that concludes the lesson for 8.9. Go to my math lab and complete your exercises there. And I'll see you next time.